Hello everyone, I'm Donghyeon Lee. I'm a master student at Sungbuk National University in South Korea. I'm going to introduce our research on pruning from scratch via shared pruning module and nucleonome-based regularization. Before we move on to our method, let's outline a traditional pruning pipeline. We initially train a large network starting with initial weights. After completing this training step, pruning method is applied to determine less important channels. Afterwards, the pruned network goes through a fine-tuning process to recover the performance loss that occurred during the pruning process. However, the process of training a large network takes a lot of time and resources to achieve convergence. Next, after fine-tuning the pruned network, it needs to remove unimportant channels through a reconfiguration process to achieve real acceleration. During this process, we need to be careful when dealing with shortcut connections that are commonly used. The reason is that it can cause channel alignment problem. Channel alignment problem is a significant drop in performance after removing unnecessary channels due to different dimension or indices between layers involved in shortcut connection. To solve this problem, it can utilize channel union technique, but the size of the network may increase. To address the aforementioned issues, we introduce our approaches. First, to minimize training resources, we employ pruning from scratch pipeline. Second, we propose a shared pruning module to solve the channel alignment problem automatically. Lastly, we introduce nucleonome-based regularization to minimize performance degradation during pruning. Now, let's go through them one by one. Instead of using a traditional pruning pipeline, we prune the network from the initial weight to improve overall efficiency. Next, to avoid increasing the network size while addressing the channel alignment problem, we propose a shared pruning module. The pruning module consists of pruning indicators that determine which channels to prune. Previously, the pruning modules were applied for every layer individually. This causes channel alignment problem during the reconfiguration process as depicted in part B of the figure. Therefore, as you can see in part C, we solve this problem by introducing a shared pruning module for the layers involved in shortcut connection. This enables performance to be maintained and prevents increasing network size during the reconfiguration process without using the channel union technique. Next up is nucleonome-based regularization. Since network pruning removes channels, there is an inevitable performance drop. We propose to prune using nucleonome-based regularization to minimize this loss. Before we talk about nucleonome, let's talk about rank. In mathematics, we often use rank to measure the expression capacity of a matrix. However, rank is the number of non-zero singular values. Therefore, it is hard information. Otherwise, nucleonome is the sum of the singular values, which can represent capacity with soft information. That's why we use nucleonome-based regularization to preserve the network expression capacity. Specifically, as shown in this figure, we minimize the difference between the original network's expression capacity and that of the pruned network. To summarize, the loss function we utilize is as follows. First, we utilize cross entropy as classification loss. Second, to compress the network to the desired compression ratio, we use MAC-based regularization loss. We also add nucleonome-based regularization loss to maintain the expression capacity. Here are the results of our experiment with the proposed method. We conduct experiments on CIFAR10 and ImageNet to check the performance on different sizes of datasets. On CIFAR10, we achieved the highest performance of 93.5% without pre-trained weight, requiring less computation than the other method. Similarly, we achieved 75.3% accuracy by pruning from scratch over 90 epochs, requiring less computation than the other method on ImageNet. Next up is the ablation study. The following experiment shows the impact of our proposed regularization loss. In the following graph, you can see the size of the MAC-based regulation loss and the nucleonome-based regulation loss during pruning. The MAC-based regulation loss is large at the beginning of the pruning to compress the network, and then the nucleonome-based regulation loss contributes to improve expression capacity. Here is the result demonstrating how nucleonome-based regularization affects network structure. The following experiment compares networks without and with nucleonome-based regularization loss. The two networks have similar computations. A noticeable feature is that when nucleonome-based regularization loss is used, there are more channels in the layer involved in shortcut connections as depicted hatched bars. This suggests that the layers involved in shortcut connection are more important for maintaining performance than the layers that are not. This table shows the computation of the network before and after the reconfiguration process. As you can see in this table, our method can reconfigure without increasing the network size, unlike the previous method. Now, this is the conclusion. We introduced a shared pruning module to automatically deal with the channel alignment problem. We also proposed a nucleonome-based regularization to improve the performance. Our proposed method can achieve high performance with less computation without any pre-trained weight on CIFA10 and ImageNet. We also show that the network can be reconfigured without increasing network size. Thank you for listening.